Okay, welcome to the second lecture in Demography 145, History 139b. I am supposed to announce for the first 2 weeks that this course is screencast, which means that the audio portion and what's on the screen will be available for downloading at some point. You'll be disappointed if you download Wednesday's lecture because there was no audio, because I didn't turn on the microphone. Okay. Before we start, a couple announcements. I'll ask me to clarify that the lab reports are both a group project and an individual project. Everybody needs to turn in both slides that are produced in your group of 3, and you'll have a few minutes after class to form groups, and also a 272-word essay that is your own work. Right? And it's very important to me that it be your own work. So you work together on the slides, then you separate and work alone on that very long 272-word essay. Okay, is that clear? Okay. All right. I noticed that all by myself that BSpace for some reason has not included the students who have registered for 139 on the site roster. So I've asked them to fix that. But as a result, you may not have gotten the email, or you may have gotten the email that I sent on Thursday, only this morning. That email reminded you not to go to section on Thursday, and also to take a look at the Sapolsky reading that was downloadable from the website. And how many got a chance to look at that reading? Excellent, excellent. Okay, if I had been in a malevolent mood and felt like giving you an unannounced quiz, the quiz today would have been, what animal did Sapolsky write about? Okay, not hard. Okay, it's a very difficult quiz if you're not here, and particularly not here on time, but not a hard quiz. Anyway, not going to give that quiz. But I really like that article because it brings to mind one of the main points of the lecture today, which is on world demographic history. The point, its main point of the article, I thought, was that it's kind of neat that young people are reckless. There actually is an upside. But it also brought out a biological need for migration, and that is that organisms, animals that live in small groups, such as human beings during most of our evolutionary course, need to exchange one sex with other groups in order to avoid inbreeding. Right? So one of my points here is that migration is crucial to human evolution. That's one of the ways. It's not the way I was going to stress today, but it's an interesting way, and it's an important way. And one of the things I hope you have time to mention is among humans, it's not the males but the females. The genetic data indicates tended to leave their group of their birth and join a different one. So among humans, it's women who are reckless, despite what the auto insurance companies think. Okay. So the main points that I want to make are basically this: that first, that migration is really important. That demographers study migration right alongside fertility and mortality because it's that important. It's that fundamental to the human condition. Just like fertility, it is a mechanism that humans have used throughout our evolutionary course and today to equalize population, to rationalize population and resources. And that story I'm going to tell in several different ways today. Also, because of the way migration worked and because of the geography, I'm going to touch on this important story, which is why it was that Pizarro, for example, with about 80 Spaniards, was able to conquer 25 million or so Incas, rather than Atahualpa sailing to Spain and doing the same to the Spaniards. It's a question that Jared Diamond raises and offers some answers, and I'm going to rehearse those for you because I think they're important and also quite interesting and critical to the way our story, the story of migration to the United States, begins. Right? All right, so outline. We're going to start by talking about the big picture of population growth, which we'll call the 3 humps of human history. We'll talk about human origins and migration. That's the young and the reckless story, but not really the story, but the other story that goes with the young and the reckless. And the old world versus the new world, the Atahualpa story. Before we start, though, are there questions or anybody questions or comments about the Sapolsky reading or about anything else that has come up, administrative or substantive? Okay. Feel free to interrupt with questions as we go. In fact, be encouraged. Okay. So until this year, last year, I would have shown this slide, Lucy and the hominids. But Lucy has been displaced as of last year by a new hominid named Ardi. Ardipithecus ramidus, who was discovered something, I guess, a decade ago, but it took a very long time to separate the bones from the fossils. Ardi displaces Lucy somewhat in the history of humans, but certainly not entirely. Ardi's not the oldest hominid that we found, but it's the oldest one about which we know a lot. There were about 36 individuals who were part of this archaeological find. I mean, the bones of 36 individuals. So quite a lot is known. The big issue with Ardi is not that she's only 3 feet tall, but bipedalism. This is the part of human evolution, or one piece of human evolution story that makes migration so important. Development of bipedalism obviously makes humans more mobile because it allows us to walk on 2 feet. Ardi is a little bit uncertain about bipedalism. As you can see mostly from that big toe. Unlike Lucy, who was found a million years later, and not only bipedal but has footprints. So historians of demographers of migration like to say that she was the first migrant. Ardi's clearly taking that first step towards bipedalism, but it's a fairly halting step. It will take a while before it's perfected. About a million years, in fact. Right. So whether or not Ardi is the ancestor of the first bipedal hominid is fairly debatable, largely because what it means to be human ancestors or the ancestors of Homo sapiens isn't as obvious as many people tend to think. In this common illustration, which Darwin would never have approved of, it's terribly ironic that it's on his book cover, but I guess when you're dead, editors will do what they want. This image of evolution as a linear path from apes to humans is not at all how it occurred. The model that Darwin speaks of as natural selection is more like the branches of a tree. So we have common ancestors with Ardi, no doubt. We have common ancestors with chimpanzees further into the past. But there's not a sense that you can put Ardi here and then my brother there. It's a much bigger network. And there were lots and lots of hominids that lived together at the same time. At the very least, when Homo sapien was during Homo sapiens' early period, there were Homo erectus was still around, so was Neanderthal, and so was Homo florensis, the one that was recently discovered in Indonesia. So it's a very different story, but nonetheless an interesting one. I'd like to turn, however, to what we know about Homo sapiens. Right? You don't need to write this. I mean, I'm in favor of taking notes, whatever helps you study, but you'll be able to download these from the website as well as stare at them, for an hour with the audio. Right? What we know, what we think we know about Homo sapiens the first 140 or so thousand years, was that they evolved in a warm climate. In fact, Homo sapien evolved in Africa. Not all hominids did, but Homo sapien did. We know that, for one thing, because of our relative lack of hair, some of us more so than others. We also know that humans enjoyed a complex diet, and that turns out to be more important than it first appears. Among other authors, Michael Pollan talks about this in The Omnivore's Dilemma. He tells it in a really nice way. But others have also pointed out that the need to eat complex foods feeds the brain. I mean, if you have a big brain, which is what humans think of themselves as being all about, you got to have a complex diet because you need all kinds of fancy molecules to do that. But in order to find all those fancy molecules, you need a bigger brain. So there's sort of a virtuous circle. You eat a varied diet, you grow a bigger brain makes you able to survive, but you need that to find all those nifty foods. We also know that humans lived in groups, and this too has this virtuous circle aspect to it. Living in groups is more complicated than living by yourself. You need to pick up very complicated social cues. You need to figure out what other people are thinking, and that's not something that your cat can do. We like to think their cats can, but they really can't. It takes, again, a big brain to do that, and once you have a big brain and you're doing that, it allows you to live in large groups, and living in groups is also adaptive to survival. Migrated everywhere. This we know from the fossil record. We also know, interestingly, from more recent genetic work on mitochondrial DNA and also on evidence from Y chromosome. I'll show some maps later. But that kind of goes well with eating a varied diet for reasons that we'll get to shortly. As mentioned previously, we coexisted and competed with other hominids. That is, it was not this linear pattern that we may have learned about in grade school. It was a network of different creatures trying out the world and mostly deciding not to persist. And we also know this. We also know that population grew slowly. And this is the fact that I told you we would derive from the trivia answer. Remember the trivia question, how long have humans been on the planet? And the answer appears down here, 150,000 years. It wouldn't matter if we used 200,000. That would be just as good an answer. That's roughly when the oldest fossil. And as I said then, this is a fuzzy number because you find a skull and you date it. Hard to prove that it's this particular hominid, not some other. There are not clear boundary lines between different characteristics. But this is the agreed upon number. So if we know, well, let's start first with this very simple equation, which anyone in econ majors have probably seen before, except instead of P, we probably use Y. For income, I mean money. This is the equation of exponential growth, which is the equation that describes the growth of populations that reproduce themselves, as money does in a bank account, or as human beings do, or as any organism that reproduces does. And it's a simple equation. I don't want to belabor it. This is as much math. This is the hardest math you'll ever do in this class. If exponentiation means nothing to you, you can safely look out the window and tune back in a minute. But simply plugging in the numbers that we know, 6.5 billion is the current population, more or less. The population 150,000 years ago was at very least 2. Right? Could have been more, but it was at least 2. So we can plug in this calculation. 6.5 billion equals 2 times e to the r, which is the rate of population growth, times 150,000 years. And if we plug that in, we find that the growth rate was about 14 hundredths of a percent per year. 14 hundredths of a percent per year. So that would mean that if there were 2 people alive 150,000 years ago, then 146,250 years ago, there were 4 people alive. Right? Obviously, that's not right. But it's right in spirit, and it's right mathematically. It's an estimate, but that absurdity is just because there really were more than 2 people alive. The point is the population was, for all intents and purposes, stable for a very long time. If you take the whole 150-year span and just take an average growth rate, which is what we calculated here, an average growth rate, it looks like human population has been sitting still. Does that strike anybody as wrong? It should, yeah. Right? If this is the case, then let's see. 4,000 years ago, the world's population would have been what? If it's 6.5 billion now, 4,000 years ago would have been about 3 billion. But we all know that the population was 3 billion in 1974. And I don't think that was 4,000 years ago. Right? How to solve this mystery? Okay, I can see you're all riveted. Obviously, growth hasn't been constant. Growth of human population has taken this shape. And this graph, which I call the 3 bumps, or sometimes the 3 humps of human history, bears a little bit of careful examination. Okay? Before we try to interpret it, notice that both the y-axis, okay, it's just dead now. The y-axis and the x-axis are on a log scale. Right? So taking the logs, although the numbers are not logs, are not shown as logs. The numbers are the actual numbers. You can tell it's a log scale because the distance here from 10 to 100, okay, a factor of 10, is the same as the distance from 100,000 to a million. Right? That's the same amount of space. So it's not linear. It's increasing rapidly as we go. And this is a useful way of showing information for a really, really, really long time period. If we just had plain old million years here unlogged on the scale, you couldn't see any of these bumps. The population would look like it would be completely flat all the way to the very end, and then it would be vertical. Right? Because the way human population has gone over the vast stretch of the past, the population has been growing very slowly, but over the last few hundred years, it's grown quite a bit more rapidly, especially in the 20th century. Right? So we shot way up. So it's log scale on years, and it's also log scale on population. Right? So again, the first tick mark there is that 10,000 up to 10 million, and then 10 million to 10 billion is the same. Although that's not obviously 10 billion, is it? Right, I guess it's 10 to the 10. Okay, it does look right on the screen anyway. So again, it's a log scale. It takes a little bit of getting used to, but not too much. And just remember that as you go up and as you go to the right, numbers are getting bigger much faster than linear. Okay, so this wiggly red line indicates a period when we're not so sure we're talking about Homo sapiens anymore. Right? As we go back beyond there, we may be talking about Artie and his pals. Actually, we're not, because he's 4 million years ago, but various other species that have a lot in common with us, but are not necessarily anatomically modern humans. It's dotted line, this first hump, because I'm making up all these numbers. Nobody was taking a census back then. We don't really know. The 4 million is based on a calculation of carrying capacity, because this dotted line is hunter-gatherers. The story here is that over this first hump, we're talking about people who are engaged in a hunter-gatherer lifestyle. Right? And I have a picture to remind us these aren't actually hunter-gatherers. This is some museum diorama. Maybe I can figure out how to turn this off. There we go. Can we see better now? I'll turn that off so you can hear better. It's just some museum diorama. It's not really correct. It's a mnemonic device. It reminds us that we're talking about hunter-gatherers here in that first the first hump. Okay? And hunting and gathering is what most of our ancestors did for most of the distant past. They lived as hunter-gatherers in sparse nomadic populations, that is, those small groups. They had a variable and healthful diet that would make Michael Pollan happy. They had minimal specialization and minimal accumulation, by which I mean they moved around, so they didn't have everybody did the same thing, hunt or gather, and they didn't acquire a lot of stuff. Okay? They also successfully adapted to every ecological zone on Earth except for Antarctica and maybe the tops of some very high mountains. But what happened during this period is, as the population grew towards 4 million, hunters and gatherers needed to move. The population density that supports hunting and gathering is on the order of 1 to 0.1, 1 person to 1 square kilometer, roughly. Where there's more rainfall, it can be a little bit higher. By lakes and rivers, it can be 10 times that. But it's roughly a person per square kilometer. So as population grows, even though it's growing slowly, it's growing over a long time, as population grows, hunters and gatherers spread out. And I'll show some maps about that shortly. What do you think the second hump is? Yes? Very good. Here's your imaginary chocolate. Exactly, agriculture. And agriculture is kind of a big deal, right? Agriculture catches on in various places, and I'll go through where and when in a second, at different times. And the way it catches on in different places, or the way it's developed in different places, has a lot of impact on our story about North America. Here's a little picture showing how fun agriculture is. From the immediate spike in the population, you might think, wow, agriculture, when someone invented that, everybody just jumped on the bandwagon, started having farms and babies. And to some extent that's true, because we're on a log-log scale. In fact, agriculture caught on slowly because it wasn't obviously a good deal. This looks more like a vacation than this does. And there's a reason for that. Hunters-gatherers at their, at below carrying capacity, that's not a bad life. It's been calculated that it takes fairly little effort to actually produce subsistence. It's a low level of subsistence, but it's also a low level of effort. So this, at least some anthropologists believe there's a fair amount of leisure in this society. In agriculture, that's not the case, and especially early in the transition. The evidence from bones tend to indicate that where hunter-gatherers and early agriculturalists coexisted, generally not happily, the hunter-gatherers did better. They had thicker bones and bigger smiles, I guess. Nonetheless, there are advantages. The diet for agriculturalists is much higher in calories. It's not as much variety, but it has a lot of calories. It tends to be, of course, 1 or 2 crops, or a small number of crops. So it gets you a monotonous, calorie-rich diet, but you also get famines, because more and more people are dependent on the weather. And you also get infectious diseases, because people are packed more closely together, but also because of animals. Again, talk about that later. Nonetheless, for all its drawbacks, the age of agriculture certainly brought with it very, very rapid population growth, at least for a while. But unlike this very smooth dotted line that I made up for hunter-gatherers, the jagged line indicates something very different going on as the agricultural era comes towards an end. And that is exactly what I just mentioned. It's famine and disease. Because of the dependence on of greater and greater populations on more and more marginal land, and because of infectious diseases, we know from here we're getting into the era of written records. We know from family reconstruction data that there were much more frequent periods of high mortality that appear in the agricultural period, certainly than the industrial period that comes next. It's hard to say for sure about the hunter-gatherer period, but it appears to be. It appears that is the case. That this is the period when Thomas Malthus is writing about. And while some people say that Malthus is wrong because the world has not evolved into starvation yet, if you look backwards from where Malthus was standing in the late 18th century, he was completely right. He could see the checks on population. And the last era, of course, is the industrial. Right, here's Charlie Chaplin to remind us of how fun that is. We'll be talking about the Industrial Revolution quite a bit in this class, but not for a while, because we've got the colonial era to deal with first, and then the pre-industrial era. But it follows the same trajectory here as the agricultural era. Again, something changes, and population again grows. In all these cases, it's essentially the same story. Population reaches carrying capacity, it bumps along, and then something changes. Technology changes.